Now let's talk about the effect that the second derivative has on the shape of a graph. So let's consider three graphs that are all increasing on some interval and all have the same 2 points, start and end at the same place. And I want to look at three different ways I can kind of increase from one point to the other. The most straightforward way would be to just take a straight line between those two. But I could also have that curve sort of bend below the straight line or bend above it. So in all three cases, f is increasing on that entire interval. And f increasing means that f prime is positive. So the first derivative doesn't help us to distinguish between these three curves. So how can we distinguish? Well, notice that in the first case, since I have a straight line connecting them, that f prime, in fact, is constant. Right? The f prime is about the slope, and so the slope is the same at every single point because it's a line. And that means that f double prime, the derivative of the derivative, must be 0 on this interval, because the derivative of any constant function is 0. In the second case, the slopes are changing. You start off with small positive slopes, and then you end with large positive slopes. So in other words, f prime is increasing. Right? It's not only positive, the slopes are always positive, but they're also increasing and becoming more positive. And to say that f prime is increasing is to say that the derivative of f prime is positive. So on this interval, f double prime is positive. And finally, in this last case, we start with a large slope, and then we end with a small slope. So that means that f prime is decreasing. And so f double prime is negative. So we see that information about the second derivative helps you to distinguish between these three basic ways of increasing from one point to another. Okay, so let's make that a little bit more concrete. So what we have is that if f double prime is 0 on an interval, say on the interval from A to B, well then f is linear on that interval. So in other words, it looks something like this, or this, or this. If f double prime is positive on the interval from A to B, well, that means that f prime is increasing and we say that f is concave up. Well, roughly speaking, if f double prime is positive, then your graph is going to look either like this, or like both of them kind of put together. So in the first case, what happens is I have a large negative slope at the beginning, and that large negative, like maybe that's, say, -5, is becoming closer and closer to 0. So I'm increasing from -5 to 0. Whereas in the second half, I'm sort of increasing from 0, or a small positive, to a large positive, like 3 or 4. And in this last case, I'm just going through the whole range, from large negative to small negative to 0 to small positive to large positive. And well, finally then, if f double prime is negative on the interval from a to b, that means that f prime is decreasing and that f is concave down. And so those pictures look just like the upside down versions of these ones up here. So it's going to look something like this, or both. Okay, so information about the second derivative tells you about how your curve bends, roughly speaking. Does it bend upward, and if so, how sharply? Does it bend downward? Or maybe it doesn't bend at all, and it's just a straight line. And finally, let me highlight one last thing, which is what we call inflection points. So we say that f has an inflection point at some x value c if f double prime of c is 0 and f double prime goes from positive to negative, or vice versa, at c. So what does that look like? Well, an inflection point could look something like this. So if you look at the left half of that graph, you notice the graph is bending downward. It looks kind of like an upside down parabola. And the right half looks like a right side up parabola. And so this point here, sort of in the middle, is the point where it switches concavity. So that's the inflection point on this graph. So sometimes they look kind of like that. One that crops up in a lot of contexts. So if you have this sort of S-shaped curve, this is typical of certain kinds of population growth. It also looks a lot like a sort of a pH curve. And again, this point sort of here in the middle, it's sort of, the curve was bending upwards for a while, and now it's starting to bend downwards again. So that's also an inflection point. Okay, and then just like what we did with the first derivative, if you have a function and you want to find where it's concave up and concave down, and then find its inflection points, well, you just take the second derivative and find where it's positive and negative. So maybe let me do that for the same function that we looked at in the last lecture. So let's determine where the function f of x is x cubed minus 9x squared plus 24x is concave up and down. So f prime is 3x squared minus 18x plus 24. So f double prime is 6x minus 18. And we want to know where is that positive and negative. So we find where that is equal to 0. That happens at x equals 3. And then in this case, f double prime, if I plug in something that's less than 3, for example, f double prime of 0, well, that's something negative. Whereas f double prime is something bigger than 3, like 4 or like 1,000, would be bigger than 0, so that's positive. And so we find that f is concave down from negative infinity up to 3, and concave up from 3 to infinity.